Welcome everyone to this presentation of the paper Energy Analysis of Lightweight AEAD Circuits. My name is Andrea Caforio, and this is a joint work with Fatih Balli and Subhadeep Banik from the LASAC lab at EPFL Switzerland. We are currently in the midst of the NIST LWC lightweight standardization process that is seeking a new standard for AEAD schemes. More specifically, we are at the end of the second round and the finalists are due to be announced later this year. Although it is a NIST standardization process, the discipline of lightweight cryptography is rather ambiguously defined. For example, this term comprises a multitude of disciplines such as circuit area, latency, throughput, power energy optimizations for hardware implementations, or instruction count or memory size for software primitives. This ambiguity is reflected in the pool of candidates that are still competing. So at the moment in the second round, there are 32 remaining constructions, and they are based on various paradigms. For example, we have block cipher-based constructions, stream cipher-based constructions, or other constructions that are based on a keyless permutation. In this paper, we are going to focus on 10 of those schemes, namely Fork AE, Gift Combined Feedback, Hyena, Lotus and Locus, Pitchamask, Romulus, Saturnin, Skinny AED, and Sunday Gift. All of those 10 AED schemes are bootstrapped via lightweight or semi-lightweight block ciphers that are efficiently implementable on ASIC circuits. Naturally, our selection excludes constructions that are permutation-based, AES-based, or based on stream ciphers. Let's look at the candidates in more detail. So we have 3 schemes that are based on the Gift block cipher, namely Gift Combined Feedback, Sunday Gift, and Hyena. 2 schemes use a tweakable variation of Gift with a 64-bit block cipher, namely Lotus AEAD and Locus. Then we have 2 constructions that use the largest variation of the tweakable block cipher Skinny. Then Fork AE uses a Skinny derivative they denote by Fork Skinny. And finally, we have 2 candidates, Pitchamask and Saturnin, that use dedicated block cipher constructions specifically designed for the competition. A quick glance over all of the NIST LWC submissions will reveal that most of them don't really focus on the energy metrics, but prioritize the circuit area or latency metrics. This has various reasons, but maybe the most poignant reason is that there exists a multitude of ways a block cipher algorithm can be mapped to a congruent circuit. For example, a designer might choose to unroll the round functions. So we say that a block cipher circuit is R-round unrolled when R-round function invocations are computed in a single clock cycle. Similarly, we say a block cipher is fully unrolled when it performs one full encryption in a single clock cycle. This is depicted in the figures below here. Let's say we have a generic block cipher composed of a key state, a data or plaintext state, and a round constant state. And now we want to unroll it twice. So we want to compute 2 round functions in a single clock cycle. This means that we have to serially chain the key schedule, the round function, and the round constant components such that we can achieve such a feat. Of course, this generalizes arbitrarily to any unrolling factor R. In a paper by Banik presented at SAC in 2015, it was shown that the energy consumption of unrolled block cipher circuits conforms to a quasi-quadratic equation given by this expression here. We say that E, the energy, as a function of the unrolling factor R, is a product of the average power consumption which is given by this quadratic equation where the constants A, B, and C are based on the circuit components, such as registers, multiplexers, or arithmetic components, multiplied by the latency to the number of cycles it takes to perform one single encryption. Another technique that is well used in electronics to reduce the actual energy consumption of a circuit is clock gating. So let's say our circuit has some registers that are idle for vast periods of time. If those registers are connected to a clock signal, they drain unnecessary power. So it seems logical that whenever a register is idle, so it doesn't compute anything or is not involved in any computation, we should decouple it from the clock signal, thus saving some energy in the process. A more specific technique for unrolled block cipher circuit is inverse gating, which was invented by Banik and others at Host 2018. So this technique reduces the propagation of glitches between subsequent rounds. So a glitch produced at the end of one round function only is compounded in the round function that follows. So we want to decouple the round functions as long as the signals at the end of one round function is not stable. So what are the actual contributions of our work? So first, we perform an in-depth exploration of the effects of generic implementation techniques, as shown before, on the energy consumptions of our selection of AEAD schemes. And in the course, we identify the optimal circuit configuration for each candidate. This allows us to provide a fair evaluation of the selected schemes with regards to all hardware metrics. Furthermore, we demonstrate that the optimal choice of the unrolling factor R depends on both the complexity of the underlying block cipher and the complexity of the surrounding circuitry that implements the AEAD mode. And finally, in a last effort, we investigate threshold implementations against side channel attacks of the candidate pool and investigate their effects on the energy consumption in general. So let's get to the meat of the paper. So in order to facilitate a fair evaluation of the candidate pool, they need to be implemented under a common API. So this API should be feature complete, meaning that it should be able to process incomplete or empty AED and message blocks. However, we differ our API from the well-known established CISA API in the fact that we demand that blocks which are incomplete are padded externally, for the simple reason that padding components in a circuit are relatively involved structures, so they may skew the actual energy metrics of a construction. So how does this look like in practice? So we have an AEAD component, and that is given the signal, of course, a clock signal, a reset signal, then signals for the key, the nonce, and the data. Then we have two control signals signaling whether there is no AED block or no plaintext block. And finally, we have some signals, control signals, that signal whether we are processing the last AED block or the last message block. So how does this actually look in practice? Let's look at the GIFT combined feedback mode of operation. So on the left, we have the combined feedback mode of operation, which is a rather simple mode where we have a serially chained series of encryption calls that are interweaved with a linear function G, and in the midst we mix in the AD and message block and some round constant L. So how can we map this to a circuit, which is relatively straightforward? We have the GIFT component. We need an auxiliary register that holds the round constant L. And then due to the structure of this mode of operation, it's actually possible to share the block cipher state with the overall AEAD state. So we don't need any additional register that holds the AEAD state. So this is not possible for all schemes. Naturally, in order to actually extract sensible energy metrics, we need to synthesize all of our circuits. For this, we use the TSMC 19 nanometer cell library process in combination with the Synopsys design compiler for synthesis. Then, the power estimation is performed through back annotation of the switching activity in post-synthesis using the Synopsys power compiler. In order to get an accurate power estimation, our test bench is rather large. It comprises more than 500 AEAD blocks and more than 4,000 message blocks. Finally, we compute the energy per 128-bit block as the multiplication of the average power times the overall time it took to run the entire test bench divided by the actual number of blocks. So let's look at the effects of our design choices on the energy consumption. Let's start with the clock frequency. So the power consumption of a CMOS circuit is composed of a dynamic component. This is the switching activity, including all the glitches, and a static component. So this is mainly the balancing of the inherent leakages of gate capacitors. And it is a well-known result that or occurrence that in low leakage environments and at high enough frequencies, the energy consumption of a circuit is independent of the clock frequency. This is easy to see since the power consumption is inversely proportional to the latency, so the number of cycles, if you vary the clock frequency. So to drive this point home, we did a little experiment with an AES-128 circuit in a single round configuration, and we can clearly see that the energy consumption seems to stabilize at higher frequency, and we also see that the contribution of the leakage power is becoming negligible as we increase the clock frequency. So let's look at the effects of optimal unrolling, or at how unrolling actually affects the energy consumption. So for most or for many lightweight block ciphers, we have the case that they attain their point of energy optimality at R bigger than 1, so for multiple unrollings. For example, if we take the present block cipher, we have the following expression. So we substitute the actual component numbers for the constant A, B, and C. And if we now vary the unrolling factor, we see that is actually optimized for R equals 2. So if we now assume that present is used in an actual mode of operation that brings some auxiliary circuitry such as additional registers or arithmetic coupons, we need to adapt our expression. Since those additional components are independent of the actual unrolling factor of the block cipher, they can only add to the constant term in our expression. So here we denote it by alpha. For example then, if we vary alpha to be roughly 4, we see that our expression E as a function of R is actually then optimized for R equals 3, and not as we have seen before for R equals 2. So what does this actually mean for our pool of block ciphers? So let's, for example, take those which are based on the GIF block ciphers. The GIF block cipher is energy optimal for R equals 2, but if we actually measure the energy as a function of the unrolling factor, we see that only the lotus and locus are adding actually enough additional circuitry as part of the mode of operation such that it actually shifts the point of optimality to R equals 3. For the others, like gift combined feedback, Sunday gift, or hyena, which is very similar to gift combined feedback, the point of optimality remains at R equals 2. Then let's look also at the effects of clock gating. So naturally, clock gating works best for construction which have many auxiliary registers that run for many clock ciphers or remain idle for many clock ciphers. On the other hand, the effect of clock gating is negligible for simple modes of operation like gift combined feedback, which only has one small additional register that hold the round constant. and Sunday Gift, which has no additional registers at all. So in the graph we can see that for constructions with many auxiliary registers like Lotus, Fork AE and Skinny, we can save up to 1/3 of the energy if we clock gate the idle registers. So let's compile all those results. So we see that most of the constructions are actually optimized in a clock-gated way at an unrolling factor that is bigger than 1. We have seen that both locus and locus are actually optimized for 3 unrollings. And we also see that actually some of those constructions are actually optimized for in the fully unrolled version. This means that the block cipher computes an entire encryption in one clock cycle. So what does this mean in summary? So this plot plots the overall energy consumption per block for all the investigated schemes, and we can see that the most energy efficient schemes are really the gift-based ones. So the chart is dominated by gift cough and hyena, which are very similar. You can also see that some more involved instructions like Fork AE or Saturnin don't fare so well. On the other hand, we have constructions like Sunday Gift, which is a very simple mode of operation, but requires that the message blocks are processed twice, so which naturally then drives up the energy consumption. So although Sunday Gift is even simpler than gift combined feedback, its energy consumption is higher due to this higher latency. And finally, we can look at what inverse gating actually means in terms of the energy consumption, and it really shows that inverse gating is a great unifier. It almost equalizes the energy consumptions for all schemes, except those schemes which are difficult to actually unroll, such as Fork AE or Romulus. So to wrap this talk up, let's quickly look at the effects of threshold implementations. So what we did, we implemented our schemes with a single order threshold implementations with either 3 or 4 shares. And we observed that throughout all the candidates in our pool, the 4-share implementations are more energy efficient than the 3-share variants. And this is due to the fact that the latency gain we have with 4-share implementation actually supersedes the power increase caused by the larger area footprint. So in detail, this means that, as I said, for most of them, or basically all of them, the 4-share implementation, which has a lower latency but a higher area footprint, remains more energy efficient than the actual 3-share implementations. So in conclusion, this paper is by date the most detailed energy study in the realm of block ciphers. We propose a generic energy model for AEAD schemes based on block ciphers, and we provide probably the first fair evaluation of a pool of NIST LWC candidates. In terms of future work, one can argue that the TSMC 90 nanometer cell library is rather outdated, but it still remains rather popular for reporting hardware results in cryptography. But one might ask the question if similar results are possible or reportable for smaller, more modern cell libraries. And then, of course, this paper only focused on schemes that are actually based on lightweight block ciphers, but we can ask, are similar results possible for the remaining candidates that are not based on lightweight block ciphers? So this slide concludes my talk. I thank you very much and goodbye.